Hey guys, welcome to my YouTube channel. In this video, I'm going to discuss beta distribution and exponential distribution. In my previous video, I discussed joint contrast random variables, and the video before that, I discussed gamma distributions. Now, originally, my plan was to discuss exponential distributions in the video in which I discussed gamma distributions, but then the video became 45 minutes long, and I didn't want to extend the video any further. So I thought of discussing exponential distributions along with beta distributions in some other video. So this is the video in which I discuss the expected value, the moment generating function, and the variance of exponential distributions along with the expected value, the variance, and checking if it's a valid PDF or not of the beta distribution. Right? So let's just start now. So let's start with exponential distributions first, and then I'll discuss this beta distribution. So let me just write the PDF of exponential distribution, which is fx exponential distribution. Sorry for my handwriting. Right? Sorry for my handwriting. So now the PDF is fx is equal to lambda e to the power minus lambda x greater than 0, x greater than equal to 0. Actually it doesn't matter because it's a contrast distribution, right? So it doesn't matter if we include 0 or not. The probability at a certain point will always be equal to 0, and 0 if x less than 0, right? So we know that the domain for the exponential distribution is all positive values of x, right? Now we'll be finding the expected value, the variance of this exponential distribution, the MGF, the moment generating function, right? So first of all, let's just check the PDF, right? So if I just integrate the PDF over the values of x from 0 to infinity, it should come out to be equal to 1, right? Otherwise the PDF won't be defined. So now we have lambda e to the power minus lambda x dx 0 to infinity, and this should be equal to 1, right? So if I just take lambda out, lambda e to the power minus lambda x, and this becomes minus lambda 0 to infinity. So now I have lambda minus lambda e to the power minus lambda into infinity minus e to the power minus lambda into 0. This ultimately gives me minus 1, 0, minus 1, which is equal to plus 1. So we know that lambda, so we know that f of x is equal to lambda e to the power minus lambda x is a valid PDF for all x greater than equal to 0, right? And what is lambda here? Lambda is the rate parameter. So as I discussed in the video on gamma distributions, I told you guys that gamma in the gamma distribution video, I told you that this parameter is known as the rate parameter, and this is lambda. This is the rate parameter, and this, which was also present in the gamma distribution video, was the shape parameter. But here we don't need to encounter this, so I don't need to write, but just for your revision I am writing this again, that this is the shape parameter and this was the rate parameter. In exponential distributions, we are only concerned with the rate parameter. So now let's just find the expected value. For expected value, what do we need to do? We need to do x fx dx over the limits of x. So here the limits are not from minus infinity to infinity, so I'll be changing the function and I'll be writing limits as 0 to infinity. this becomes x, and fx was lambda e to the power minus lambda x, lambda e to the power minus lambda x dx. Now the expected value becomes, lambda comes outside because it's a constant, 0 to infinity, x e to the power minus lambda x dx. Now we have to apply Eilert rule here because we are integrating the function. So now e of x becomes lambda. Now Eilert says that it is a thumb rule, basically. Eilert is a thumb rule, and you should know this basic integration, right? Otherwise the whole point of this video will be defeated, right? So if I just apply Eilert, which is a thumb rule, I can take x as the Eilert, right? So I'll take x as the first function and x e to the power. I'm writing all of these basic things again and again so that you don't get confused what I did here, right? I actually know the people who are watching my videos are quite comfortable with integrals, but still I think it's better for someone who's watching the video for the first time. He or she should know that what I'm doing here, right? So x is my first function and e is my second function. So x e to the power minus lambda x by minus lambda, and lambda is a constant. This is from 0 to infinity, minus, now this is my first function, the derivative of x is 1, and e to the power minus lambda x, again the integral of this is minus lambda e to the power minus lambda x minus lambda dx. This and this becomes positive, and let me just remove this and let me write this 0 to infinity here, right? So this ultimately becomes lambda x e to the power minus lambda x minus lambda, and this is positive, and this becomes e to the power minus lambda x, and this becomes minus minus, right? So minus lambda square, 0 to infinity, right? So this gives me the expected value as, if I just multiply lambda, I'll be getting minus x e to the power minus lambda x and minus e to the power minus lambda x lambda 0 to infinity. If I just take the negative sign out, I'll be left with x e to the power minus lambda x minus e to the power minus lambda x, positive because the negative sign is outside, from 0 to infinity. Let me just reduce the thickness of my pen, otherwise it becomes tough for me to write the notations. So now the expected value becomes, now the expected value becomes, this becomes 0, e to the power minus infinity becomes 0, and again this also becomes 0, e to the power minus infinity again 0, right? And this is negative, so if I substitute 0, this becomes 0, and this gives me positive, this gives me negative e to the power minus lambda and 0 divided by lambda, right? So ultimately I'm left with the expected value is positive 1 upon lambda. This is my mean. So basically the mean in exponential distribution is the inverse of the rate parameter, right? So if I just try to make you recall, in the video on gamma distributions we discussed that the mean in the gamma distribution is equal to, the expected value is equal to the shape parameter divided by the rate parameter. Rate parameter is lambda in both of the cases, and alpha is the shape parameter, right? So now we can say that the gamma distribution, gamma, lambda which is the rate parameter and alpha which is the shape parameter, whenever alpha becomes 1, we say that this becomes exponential distribution, right? you can see that whenever alpha is equal to 1, we get 1 upon lambda, which is the mean of exponential distribution. So basically, exponential distribution is gamma distribution only with the shape parameter as 1 and the rate parameter as lambda. Now let me just move this. This was only for revision, right? And this was our actual stuff. So I'll be sharing this PDF with you guys. I share almost each and every PDF of mine in the description, so you can just check that out. Now coming back to the question. Now we need to find the variance, right? For variance we need to find ex square. So ex square becomes x square e to the power minus lambda x and lambda dx from 0 to infinity. I'm just trying to do this quickly now. So lambda, now x square e to the power minus lambda x minus lambda, I'm just integrating this function, minus 2x e to the power minus lambda x minus lambda dx 0 to infinity. Again, if I just try to do this, this gives me x square e to the power minus lambda x minus lambda, and this was positive, right? So positive 2, and this becomes x e to the power minus lambda x, and already I had lambda, so this becomes minus lambda square, and this is a negative sign, and this becomes 2 times x becomes 1, so this gives me e to the power minus lambda x, and I already had a lambda here, so e to the power minus lambda x minus lambda dx, this becomes again positive, and again this whole from 0 to infinity. Now let me just copy this and proceed further. This is one of the best features possible in Notes app, that I can easily copy stuff, otherwise I would have to write the whole expression again. Oh my god. Why did I jinx it? So we have this expression now. This is ex square, right? So ex square then becomes lambda x square e to the power minus lambda x minus lambda minus 2 upon lambda square e to the power minus lambda x, and this becomes 2 upon lambda e 1 upon lambda e to the power minus lambda x minus lambda, and this becomes 0 to infinity. So this, if I just start putting in the limits now, I'll be left with, wait a minute, yeah, so I'll just take out negative sign, negative lambda out, and if I just put the limits now, I'll be getting 0. If I just put infinity in all of these terms, I'll be getting 0, and if I just substitute 0 in all of these terms, I'll be getting 0 in the first term, yes, 0 in the second term, no, I'll be left with minus 2 upon lambda square, right? No, wait a minute, an x was also here, so 0 only. So 0 only, yeah, so a 0 only, and then I'll be left with, this was 0, so this was 0, and wait a minute, this was the infinity term 0, so this, wait a minute, so this was 0, and this also becomes 0, right? Now I got it, right? So 0 0 0 0 0, and this becomes 2 upon lambda cube minus 2 upon lambda cube, right? And this becomes 1. So Ex square ultimately becomes positive 2 upon lambda square. Right. Now we'll find the variance. Finding the variance, I'm so sorry for the calculation. I messed it up. That's why I had to do that carefully. Otherwise, we would have been stuck here and I would have to stop the video again. So now Ex square minus E of x whole square. This is the formula for our variance. So my variance becomes variance of x is so this is 2 upon lambda square minus E of x was 1 upon lambda whole square, and this gives me 2 upon lambda square minus 1 upon lambda square, which is 1 upon lambda square. So my variance of x becomes 1 upon lambda square. Right? So we have found the expected value, we have found the variance now. Now we'll be finding the moment generating function. Moment generating function, MGF. This is the expected value of e to the power tx, which is e to the power tx fx dx, and our limits here are 0 to infinity. So expected value of e to the power tx then becomes 0 to infinity e to the power tx, and fx was lambda, e to the power minus lambda x dx. Now if I just take out lambda, this gives me tx minus lambda x dx. Now this is from 0 to infinity. Expected value of e to the power tx now becomes, if I just keep lambda outside, what I can do is from 0 to infinity e, and I can take a negative sign out. So t is effectively less than lambda, right? So this gives me dx. And now if I just integrate this lambda, and this gives me e to the power minus lambda minus t x minus lambda minus t from 0 to infinity. So this becomes expected value of e to the power tx, and this is equal to lambda upon minus lambda minus t, and e to the power minus infinity becomes 0 again, and this gives me minus 1. So my moment generating function becomes positive lambda upon lambda minus t. Now this is my moment generating function, or I can write this as mxt. So if I just find the first derivative of mxt and I put t as 0, this will give me my expected value, right? So if I just differentiate this with respect to t, lambda upon lambda minus t, I'll be getting lambda upon lambda minus t whole square, and so basically lambda minus t, so this will be minus 1 and again minus 1, positive. And now I need to put t equals to 0. So this was t equals to 0, so my m dash xt becomes lambda upon lambda minus t whole square is lambda square, 1 upon lambda, which is equal to my expected value. Now if I find the second derivative and I equate t equals to 0, I'll be getting e x minus 0 whole square, which is e x square. And if I just try and show you this will be lambda upon lambda minus t whole square, so I'll be getting minus 2 lambda minus t whole cube, and this will be negative 1, so negative becomes positive, and my t should be 0 here, right? My t should be 0 here. So this m double dash x t equals to 0 gives me 2 lambda cube, which becomes 2 upon lambda square. 2 upon lambda square. So now what will be my variance? Variance of x becomes e of x square minus e of x whole square, which ultimately gives me ex square. Wait a minute, where is my ex square? Yeah, so this was my ex square. This m double dash x t conditional 0 is my ex square, which was equal to my 2 upon lambda square, right? I hope you guys can see. I know it's a bit hodgepodge, but I'll be sharing the link of this PDF in the description, so you can check that out, right? But I hope you guys can see clearly. Otherwise, my efforts don't mean anything, right? I'll try to zoom it a bit. So my variance ultimately gives me, my variance becomes 2 upon lambda square minus 1 upon lambda whole square, so 1 upon lambda square. And what is the variance of gamma distribution? What is the variance of gamma distribution? I discussed this in the previous lecture, in the previous video. So the gamma distribution has a variance of alpha upon lambda square. Alpha is the shape parameter. Alpha is again the shape parameter. Lambda is the rate parameter, right? And whenever we put the shape parameter as 1, I'll be getting 1 upon lambda square, which is the variance of exponential distribution. And what is the PDF of gamma distribution? The PDF of gamma distribution was, if I just write gamma distribution here, the PDF of gamma distribution was f of x is equal to lambda e to the power minus lambda x to the power alpha minus 1 upon m alpha, right? This was the PDF. So now if my alpha is equal to 1, what does this mean? My alpha is equal to 1. This means that f of x becomes e to the power lambda e, wait a minute, this my PDF becomes lambda e to the power minus lambda x, and lambda is lambda x, and lambda x alpha is equal to 1, so 1 minus 1 becomes 0, and this is m of 1. So f of x becomes lambda e to the power minus lambda x, and this is 1, lambda x to the power 0. Now I told you guys earlier that this m1 is equal to, so this m of n, actually this is the gamma variable, so I'm writing this as n. Basically in the books you will find the notation as this, but I have somehow wrote this as an m, and I have been writing this in such a way. So if you guys don't understand, this small m is actually this variable that you find in the books only. So this is actually drawn like this. So you draw a small m like this. So this is basically an r, like an r, but not a complete r. So this is like something like this, right? So don't consider this to be an m. But I sometimes say that it's an m, so I'm sorry for that. So this is actually equal to n minus 1 factorial, and this 1 will be 1 minus 1 factorial, which is 0 factorial, and 0 factorial is equal to 1. We all know that. So this becomes 1. F of x becomes effectively lambda e to the power minus lambda x, which is, also remember that this is also defined for x greater than equal to 0. So which is the PDF of exponential distribution. This shows that whenever the shape parameter alpha is equal to 1, the gamma distribution and the exponential distribution are the same. Now we need to discuss the beta distribution. The beta distribution. I wanted to make this video around 30 minutes only, but I think we have gone above 30 minutes, so I'll try to make this video in such a way that you guys can understand the topic as well as we can cover all of the necessary things, right? Let me just open up my notes so that I can write the PDF carefully and I don't make a mistake while writing the PDF. Other than that, I'm going to derive the whole function here. So beta distribution. So the PDF of beta distribution is 1 upon beta a comma b x a minus 1 1 minus x b minus 1, where x lies between always 0 and 1 and 0 elsewhere. Right? So let me just write what is the beta variable here. Right. So this is basically like we had gamma integral here. This is the beta integral, as I'm calling it. So this is x to the power a minus 1 and 1 minus x to the power b minus 1 dx from 0 to 1. Right. Let me just check. Yeah. Now a comma b are the shape parameters. Like we had alpha here, like we had alpha earlier in the gamma distribution. A and b are the shape parameters. Right? We can check the PDF also of this function, but before that I need to tell you something. So this a comma b is effectively equal to the beta a comma b is effectively equal to the gamma a into gamma b divided by gamma a plus b. You need to remember this. So this beta integral, I told you the value of beta integral. So beta integral a comma b is equal to 0 to 1 x to the power a minus 1 1 minus x to the power b minus 1 dx. Right? This is the beta integral. But the value of the beta integral is also equal to this, which is the gamma a into gamma b divided by gamma a plus b. Or if I write this more clearly, this is gamma a is equal to a minus 1 factorial. So this is a minus 1 factorial, and gamma b is equal to b minus 1 factorial. B minus 1 factorial. I just explained you guys right now, 5 minutes back. Gamma n is equal to n minus 1 factorial, and gamma a plus b is a plus b minus 1 factorial. Right? So now the PDF given to us is f of x x to the power a minus 1 1 minus x to the power b minus 1 b minus 1 divided by beta a comma b. A and b are the shape parameters. Let me just check. Yeah. And we also know that x lies between 0 and 1. So now let's just check if this is a valid PDF. Now we'll start deriving. Let's just check if this is a valid PDF. So 0 to 1 fx dx, this becomes 0 to 1 x to the power a minus 1 1 minus x to the power b minus 1 divided by beta a comma b. If I just take beta a comma b out from this integral, I will be left with 0 to 1 x to the power a minus 1 1 minus x to the power b minus 1 dx. This was dx, right? This was dx. We had dx here. I just missed the notation, right? And now we already know that beta a comma b is equal to 0 to 1 x to the power a minus 1 1 minus x to the power b minus 1 dx, right? I just explained you guys here, right? So from this I can say that the fx dx 0 to 1 becomes 1 upon beta a comma b into beta a comma b. This and this gets cancelled and we are left with 1. So this is a valid PDF. Now let's just move on and find the expected value from the next page. So now let's just find the expected value. For expected value we need x fx dx from negative infinity to positive infinity, but the limits here for x are defined as from 0 going from 0 to 1. So x goes from 0 to 1, x, and now my f of x is, my f of x was x to the power a minus 1, 1 minus x to the power b minus 1 dx divided by beta a comma b, which is a constant basically, so we can take that out because it has some value, right? After we integrate beta, we'll be getting some value, right? So if I just take beta out, I'm left with 0 to 1. Now x to the power a minus 1 becomes x to the power a, and 1 minus x to the power b minus 1 dx. Right. So we were discussing this only, yes. I don't know why the recording, suddenly stopped. To stop the recording. So the expected value becomes 1 upon beta a comma b. Now x to the power a, 1 minus x to the power b minus 1. So we already discussed that 0 to 1, x to the power a minus 1, 1 minus x to the power b minus 1 dx was equal to beta a comma b, and this was equal to gamma a into gamma b divided by gamma a plus b, right? Now if I have a function 0 to 1, x to the power a, 1 minus x to the power b minus 1 dx, I can write this as 0 to 1, x to the power a plus 1 minus 1 and 1 minus x to the power b minus 1 dx. This means that this will become equal to beta a plus 1 comma b. Just try to see this. We have a minus 1 here, so we have a here, right? We have a here. We have b minus 1 here, so we have b here. Here I have x to the power a, so x to the power a can be written as x to the power a plus 1 minus 1, right? So this gives me a plus 1 here, and this is as it is b minus 1, so this gives me b here, right? Now finally I am left with expected value of x is equal to 1 upon beta a comma b, 0 to 1, x to the power a, 1 minus x to the power b minus 1 dx, and this becomes 1 upon beta a comma b, 0 to 1, x to the power a plus 1 minus 1, 1 minus x b minus 1 dx, right? So the expected value becomes finally 1 upon beta a comma b. Now from 0 to 1, so this was beta a plus 1 comma b. Now if I just try to find the values, I can substitute the value of beta a comma b and beta a plus 1 comma b, right? So beta a plus 1 comma b, beta a plus 1 comma b will be, beta a plus 1 comma b will be gamma a plus 1 into gamma b divided by gamma a plus 1 plus b, and beta a comma b is gamma a gamma b divided by gamma a plus b. Now if I just divide these two values, I'll be left with gamma a plus 1 into gamma b and gamma a plus 1 plus b, and this will become gamma a plus b divided by gamma a gamma b. So this and this gets cancelled, and finally so let me just can I reduce this? No, I cannot. Let me see if I have space left. So finally, now my gamma, I would have to go to the next page. Just give me a minute. right? So this gives me expected value as gamma a plus 1 into gamma b divided by gamma, yeah. So I am left with a plus gamma a plus 1 becomes a factorial, right? So this becomes a factorial, and this becomes a factorial divided by a minus 1 factorial, and this gamma a plus 1 plus b becomes a plus b factorial. This becomes a plus b minus 1 factorial, right? Yeah. So this ultimately gives me a divided by a plus b, right? A divided by a plus b. So my expected value becomes a divided by a plus b. And why is that so? Because gamma a plus 1 is basically a factorial, gamma a plus b plus 1 is a plus b factorial, gamma a plus b is equal to a plus b minus 1 factorial, and gamma a is equal to a minus 1 factorial. Now let's just find the e to the power x square, because we need to compute the variance also, right? So if we want to find e to the power x square, we would have to find x square fx dx from negative infinity to positive infinity, but the limits here are defined from 0 to 1. X square, now fx dx was x to the power a minus 1 minus x to the power b minus 1 divided by oh, I'm thirsty, just give me a second. Divided by, this becomes divided by beta a comma b dx. So ex square gives me 0 to 1 x to the power a minus 1 plus 2 becomes a plus 1, x to the power a plus 1 minus x to the power b minus 1 dx divided by beta a comma b. This a plus 1 can be written as a plus 2 minus 1. So this gives me 1 upon beta a comma b into beta a plus 2 comma b. So my e of x square is beta a plus 2 comma b divided by beta a comma b, which gives me gamma a plus 2 into gamma b divided by gamma a plus b plus 2 into gamma a plus b divided by gamma a into gamma b. This and this gets cancelled. If I cancel this and this, a plus 2 is a plus 1 factorial, a is a minus 1 factorial. I'll be left with a plus 1 and a, right? So I'll be left with a plus 1 and a here. If I just cancel these out, and if I cancel this out, this is a plus b minus 1 factorial, and I have a plus b plus 1 factorial. So a plus b plus 1 and a plus b, right? So if I cancel these out, I'll be left with a plus b and a plus b plus 1, right? So finally my e of x square becomes a plus 1 into a divided by a plus b plus 1 divided by a plus b. This is my ex square, and we already know that the formula for variance is ex square minus e of x whole square, which gives me the variance of x as a plus 1 into a divided by a plus b plus 1 into a plus b, subtracting this from a upon a plus b whole square, right? And this gives me variance of x as a square plus a and a square plus a multiplied with a plus b and this becomes a square multiplied with a plus b plus 1. This becomes a plus b plus 1 into a plus b whole square. Variance of x then becomes a cube plus a square b plus a cube plus a square b plus a square plus ab minus a cube minus a square b minus a square a square a square a cube and a square b a square b. So I'm left with ab in the numerator and a plus b plus 1 divided by a plus b whole square in the denominator. I think I've made some mistake, but let's just see. Variance of x gives me ab divided by a plus b plus, let me write this a bit more clearly. So my variance of x becomes ab divided by a plus b plus 1 and a plus b whole square. If I just try to draw a graph around this, sorry, a box around this is my variance. Let me just check. So yes, our expected value is right, our x square is also right. So ab upon a plus b whole square, a plus b plus 1. Yes, so our variance is also correct. So guys, this was the end of the video. I hope you guys like the video. If you guys like the video, please share the video, do subscribe the channel and put in a comment. It motivates me to keep on putting in more videos. Also, I'll be sharing the PDF of my working in the description. If you have any doubts and if you think there is any discrepancy in my work, please let me know in the comments, or you can also email me at stats1304@gmail.com. Right, so thank you, bye bye, and I'll see you in the next video.